Yes. Okay, so my name is Limin. I currently at university. So my department is ECE. I also affiliate with this institution called SciLab. SciLab is not a department, people ask. SciLab does not have undergrads, PhD students. So instead, each faculty at SciLab, we are associated with this new department. So if you want to do a PhD with me, you can apply to EC or apply to CS or SCD, whatever department you apply. And then if you work with me on security topic, you are automatically a SciLab student. So it's a cross-university institution, not a department. People ask me.
You don't have your mic on.
Yeah, I think it's on.
Oh, it's on?
You have go higher.
Yeah.
Okay. Yeah, it's already on. Okay, so let's see. How many of you have taken a security class?
Wait. Can you try and speak closer to the mic, maybe like on the lapel?
This one.
Yeah, that one, yeah. On the lapel, it's not really picking up.
Yeah, okay. How many of you have taken a security class? Raise your hand and have a sample. Okay, cool. So basically, maybe 40% to half. So the beginning of this is a little bit slow because I want to make sure everybody catch up with security. So my topic is on information flow security. This is one side of security. The general theme is to make sure that attackers don't get your sensitive information, things like this. But before that, I'm going to start with more general topic. What is security, right? So this is taken from my intro to security class. I always ask students, what's your view on security? Instead of asking you guys, I'll just give you a few quotes. I also color-coded the quotes a little bit. So the first one is from the late Ross Anderson. He was a prominent computer security researcher, wrote books on computer security and from UK. He basically said security is about building systems to remain dependable in the face of malice, error, or mischance. That's one quote. The next quote is from Air Force, because I had a co-instructor who actually worked at Air Force Academy for 7 years before he moved to CMU. So that's what he grabbed from Air Force Academy. So this quote is saying that security is about ensuring systems operate properly and remain secure from outside intrusion. Right? Here's the industry perspective. Palo Alto Networks do a lot of security-related product. So on their website, they say that it's about a set of techniques used to protect the integrity of an organization's security architecture and safeguard its data against attack, damage, or unauthorized access. All right, so I color-coded these quotes because they have something in common. The things in green are about what you want to achieve. Right? So none of them actually defined security specifically, but they mentioned something they want their system to behave. Right? The first one said dependable. What does this dependable mean? It depends. The second one said operate properly and remain secure. So this is a circular definition. It didn't say what secure is, it was just the word secure. And then the third one does mention a jargon called integrity. Right? So that's one security property people care about. But the other security they care about also. So because the third one is from Palo Alto Network, they have specific product they want to push. So their definition you can see are the most technically well-defined. Right? They specifically said they care about organization, security architecture, and also data. Right? None of the other things, the other codes say what system is. From Palo Alto Network code, they actually a little more specific about system they care about. Right? So that's same thing green, right? The properties. Right? So when you do lambda calculus, you care about progress preservation. Right? So here in security, there are properties we care about, but so far we're still a little vague on the property side. And then there are things in red. What are the things in red? Anybody have answers? Yes.
Bad things that can happen?
Yeah, so bad things can happen, right? So these are attackers, right? So the green ones are properties, desired goals, security goals, properties, or policies, whatever you call it. The red one are attackers, right? So this is a very distinct view about security, right? So we have to care about not just our system. In contrast, we also have to think about attackers. That's what makes security quite interesting, in my view, right? Okay, any question about it before I move on? Any comments? All right, so now I'm going to give you about my path to security. So I did my PhD in Princeton. So my thesis is on linear type system. So I did all the progress preservation proofs, gammas, lambdas, and so on. And then I went to UPenn for a postdoc. So they are actually set through a class taught by Steve Zandwick. He was teaching security at the time. So before this, I actually don't have a clear notion of what security is. As I was going through the class, I found it interesting, as you mentioned, that you always have to think in terms of the presence of an attacker. The other thing that's quite interesting is that in the PR world, it's black and white. Here's the property, you prove it or don't prove it. That's it, right? But in security, it's not the case that you have, you know what's the best solution, you're going to deploy the best solution because you have limited budget. Right? So a company, security division in a company typically have a hard job because when they're doing their job well, there's nothing to show. When they are doing a bad job, there are attacks and bad news, data leakage, things like this. Right? So not every company are willing to pay the money ahead of time to have security. Right? So typically, this is a balanced act. They try to figure out what is my peer doing. A lot of companies think that as long as I'm not worse than what my peer is doing, I'm fine. If I get attacked, they get attacked too. So I'm not worse than them. Right? So this is like very pragmatic view of security. So even if you know what's the best approach, it's not the case that you're going to apply the best approach. Right? So for example, we know we have safe languages, Java, Rust, Python, but for companies that's willing to actually rewrite their entire code base to Rust, that's far and few. Right? The big companies have the dollars to roll out higher PhDs to do this. The smaller companies, the open source projects, we're probably not going to see movements to actually go to Rust just like that. Right? So that's the constraint in terms of budget. So the other side is that for security, when you deploy security mechanism, a lot of times not only have to pay money, you also have to pay performance. Right? So think about, I want to do an extra check to make sure that the data is doesn't include bad input of my system to run attacker code. That check is actually costing performance. Right? So a lot of the product vendors, they really care about performance. They have a thin margin in terms of sacrificing performance. Right? So in a way, the security side is a lot less black and white. It's not the case that I know the best solution, I'm going to deploy the best solution. I know there's a solution to it, I'm going to solve it because my customers are really impatient. If I deploy it, they're going to be mad, they're going to move on to a faster project, less security. Right? So this is what makes it quite interesting. I also would like to say that when I started doing this, when I taught this, I think I started maybe over 10 years ago, the common sense back then is that security and privacy does not sell product. I'm happy to say that nowadays, if you look at ads and so on, that's not the case anymore. Right? So last summer, for example, when Google said, oh, we're still going to allow tracking and serve you third-party cookies because Google is big into ads, Apple actually made an ad, essentially trolled Google, saying that our browser is more private, so on and so forth. Right? So you can see a trend now. Security and privacy does sell product, but it took a long time to actually get to where we are. We're still not at the best place that we can be. Right? Okay, so that's one side, right? So it's a bit more practical. The problems are that the attacker often break your abstraction, exploit low-level bugs that your abstraction, you wouldn't even see that behavior, for example, buffer overrun, right? So now, what can we do, right? So on one hand, we have our lambda calculus, we have our proofs, we have our way of thinking in terms of formal methods. So it turns out that in the security space, there is a reasonable intersection because the formalism and reasoning technique we can use, we learn, we can use them to model and reason about not only the security, but also model the attacker behavior as well, right? So there is a nice intersection where coming from formal methods side, because in the end, your system is like a program in some sense, right? So the attacker, it depends, right? If it's human attacker, their human behavior, we can never model. But as long as it's programmatic, we can actually use our method to model the system, define security properties formally, model the attacker, and then prove the system sound, or deploy security mechanisms, at least at some level prove design sound, knowing what assumption you made, what you omitted in our design when you only look at abstractions. Right? So we're a lot better off if we actually apply formal methods in the security world. Right? I know that some of you are doing actually formal verification, so that's definitely one important branch of security where you're going to produce a product that's secure by design. But in other fields, we're also taking a product as is, we're trying to figure out how to analyze its security properties, also try how to make sure that it can be more secure by adding additional mechanisms to them. Okay, so this is the intersection that, most of the paper kind of sort of in between. So half of my conferences, services are in the security community, the other half is in the PL community. If you write paper on security, typically you can publish on both sides depending on have a more theory angle or have a more practical application angle. Okay, so let's go back to security, right? So what we're really interested in knowing is the system secure, right? So this is not easy answer. This is not an easy question to answer. So you have to consider many things. The first thing you have to think about is what's our target system, right? So now from our form method angle, we also want to think about how do I actually model it, right? Different target system might actually have different security requirements, right? So some systems have data you want to protect, some systems you don't have data at all, right? And then you have to think about target, right? Who are our adversaries, and then you think about how can we actually model these adversaries, right? So again, in the security world, there's a notion of highly skilled attackers versus less skilled attackers. They're highly motivated ones, they're economically motivated ones, where they try to steal your accounts, steal your password, steal your credit card number for monetary gain, versus the nation-state attacker, where they're not, they're not low criminal trying to just charge your credit card. They have other motive, and their resources are sometimes we consider unbound in some sense. Right? And then, along with looking at target system, you also care about what are the security requirements, guarantees, how do you want to formalize them, right? So in the Palo networks quotation, they care about integrity of data, right? They might also you might also care about secrecy of data, not just integrity. Right? So these are, there's a set of security properties that in the field are now well defined. A lot of systems, when you are looking at a new system, you can just go to the list of properties to say, do I want this, do I want that? What data do I have? What program do I have? What kind of attacker do I have? Is this my requirement reasonable or not? And then finally, a question is, now I know what my system looks like, I know what the attacker I'm worried about, I also figured out what the security requirements. Finally, you need to figure out how to realize this security approach, right? So for us, or most of us are interested in technical approaches, meaning that we want to use safe languages, use runtime monitoring, use text system, use stack analysis, form methods, and so on, to make systems more secure. But there are also non-technical approaches, such as policy. This is actually important. Also, human factor. These areas are highly interesting in that if you look at security bugs, a lot of the big breaches, starting from human error or phishing or some such, very few attacks actually exploit highly technical bugs. But nonetheless, for us, we are more interested in technical approaches. So I do want to bring to your attention that technical approach is just only one angle of the approaches that we'll be focusing on. There are also other approaches other people are focusing on. Okay, so I'm gonna basically, the other four aspects you want to consider. This applies to security analysis. You want to understand whether the system is secure or not. This applies to you trying to make system more secure. This also applies to when you build a system from scratch, you want to build security in. Right? These are all the things you have to consider. So in the domain of, so this language-based security now is considered slightly outdated term in some sense, but people still mention it. The main idea is that we can use program languages or form methods to deal with, answer these questions, deal with four aspects of security essentially. So on the left we have the thing we want to understand. And on the right we have our methodology, right? So we are good at form modeling. We want to specify what the system looks like, what the attacker looks like. We want to specify formally what the security guarantee of the system. And then we're good at doing proofs. We're good at reasoning about if the system, based on design, actually satisfies the requirement. Right? So some work actually bring down guarantee all the way from design down to the implementation, showing that even if you go through a compiler, the binary still have the property that you care about. Right? But those require a lot of engineering work. But that's actually possible. Right? So this is basically, on the left we have concrete things we want to do. On the right we have our methodology in the program language, program method world that we're trying to apply. All right, any questions so far? Okay, so this is the agenda. I have not not given this lecture, so I don't have a good sense of timing. So let's see how timing goes. So I have 3 days. So we start with introduction. I'm done with that, and then in terms of information flow security, I'm actually going to go through several examples with you guys first, and then we'll go back to history. So that this actually dates back to the 70s. Now I'm getting a little more senior. What I observed that people don't cite paper that's actually way back when, in some sense, but it's actually beneficial to go back to read the classical papers. You actually learn more things looking at the trend of this line of research. So let's start way back then, before information security was a thing, or the beginning of information security started to become a thing first. And then I'll go into this, how do we formally model information flow security, how do we model systems, how do we specify properties, end-to-end properties, and then we'll go down to approaches, talk about how do we implement things. I'm actually going to do a very simple information flow type system, and we'll try to do a proof. This might be end of today or beginning of tomorrow. Let's see how much time we have. And then once we're done with the type system, I'm actually going to, let's see, we might have the ordering, but let's see. And then we'll go into some of the more practical concern. When you do a very strict security, sometimes this doesn't work. Then we start talking about some of the practical issues in information flow security. And then I'll talk about a little bit more additional approaches of enforcing information flow security, how to combine them, and then in the end, I'll cover more of, give you a list of applications where the field stands now, right? Okay, so examples. I'm going to start with examples. So I have like 5-6 examples. So these are all quote-unquote bad example in the sense that they're actually not secure. So I will start with a simple password manager. So let's say that the password manager have 2 kinds of data. One is the password is stored, the other one is report, right? If your password manager somehow crashes, the app developer wants the crash report to be sent back to them via a network interface. Let's just call it send in general. So I have a few snippets of code that's somehow in this password manager, right? So the first one is just give password to send. This is obviously bad, right? You don't want your password to be sent to the developer because this is your password, right? Because we want to use send to send crash reports, right? So here we have a secrecy leak. So I talked about security properties. Secrecy is one of the, security integrity are the 2 main properties. Secrecy is about keeping your data private against unauthorized users or attackers in some sense, right? So here in this scenario, my password belongs to me, right? Now, everybody else becomes the attacker. If anybody else gets my password, that's bad, right? So here, if the app just sends the password back to the application server developer, this password now goes out to people that's not me, so this is bad. This is information leak, right? This is a secrecy violation. So okay, sending it directly is bad. So what about this one? Because I can, if you know access control, you can think about maybe I should make sure that send shouldn't take password. I can only send report. And then I have this program. I'm going to assign password to report and send report. Right? This is also bad. This is the same as the previous program if you do a rewriting. Right? If you just simply say you can only send report, you also want to say that the report also shouldn't contain any password. Right? So that the specifications become a little more nuanced. Right? So these are still simple, but I'm going to give this program, this is kind of pseudocode of mixing the password with a output. I can call this crash report, doesn't matter. Let's say that this is output. User is empty. I'm picking length of the password, and then I iterate over this password. And if this is an A, I'm going to add A to the output. If this is B, I'm add B to the output, so on and so forth. Right. So this program is also bad because at the end, this output is going to be my password. This is going to be sent out. Right? So if you look at this program, intuitively, this program is bad, but seems to be a little more subtly bad. Right? I didn't directly assign. So for example, when I see this bad program, I updated my policy saying that, hey, you cannot just assign password directly to a report and then send it out. This program never directly assigned the password to the report and send it out. Right? This is somehow slightly slightly more subtle. This is a more implicitly, somehow gradually look at your password and leak it. So this is still more direct in the sense that if I'm truly being an attacker, I'm not going to just append A, right? I might actually encode A to something else. The server knows A corresponds to some other encoding, right? If I'm looking for what's being sent does not contain password, after my encoding, you wouldn't see my password. Right? There's a secret encoding the server knows. They can recover the password afterwards. Right? So this is a, I would say, somewhat sneaky program. Any question about this? So these three programs are bad because they all leak my password. Do we agree on that one? Okay, cool. Okay, let me go to the next program. This is my favorite example. When people make real-world mistakes, I like it. It makes my class more interesting. So this is, who has like Garmin Strava type of application? Yeah, so I used to use it. I don't pay them anymore. So I don't have it anymore. So the idea is that Strava is this exercise app. If I take a run, it will tell me, here's where I run, my heart rate, cadence, calories, so on and so forth. And then it also have a community, so that if I go to a new city, I can go to Strava to tell me what are the popular routes people have biked down, have run, king of the mountain, queen of the mountain, so on and so forth. Right? It's kind of fun to explore a city that way. So they will generate a heat map looking like this. So for example, here, the more brighter the color, means the more people have run in this place. So you can see here there are big roads, and then this circle looks like stadium. Right? If you're running a 400-meter, that's probably that 400-meter circle there. Right? The problem here is that there are two things. One thing is this heat map is aggregated data. Right? If they publish my run, this will be creepy because people will know where I run. This doesn't sound good. So this heat map actually is trying to address this issue by taking aggregated data. So typically people consider taking aggregated data as one way to achieve privacy. The only problem here is that this data they're taken from is from a military base. So what's the problem there? Yeah.
Now you have a map of the military base?
Yes, so it's not just me where I run is private. This location, where things in this base is also private, right? So taking the aggregate heat map only solved the issue of not leaking private information of individual users, but didn't solve the problem of sensitivity of what this data is about, right? So this is kind of a funny one. People posted this, and obviously Strava, actually back then Strava didn't even have very good permission system to begin with, or privacy setting. And after this, they overhauled their privacy setting, try to address the issue like this, right? This is also a privacy leak, right? There's some water. All right, do another example. All right, what is this example? Okay, so this is even more subtle. I'm gonna have you guys stare at this a little bit, and someone tell me what's the problem here. I'm going back to password checker. Somehow password checker number are the numbers you understand these are private. So here, this password checker is very eager. It doesn't want to waste time if your password is wrong. So here's your password, let's say on file, and then it will try to take input one character at a time. It sits in a loop and check the ICE character of the password to match or not. The moment it doesn't match, it cuts you off and then basically quit, return fail right away. It seems like it seems to save time, right? What's wrong with this program?
Timing?
Yeah, timing, right? So now, no, it's not timing. Yeah, it's not exactly timing. Any other thoughts?
Overflow?
Sure.
So you can tell how wrong you are. Like if you brute force it and it takes a little bit longer, you know you're right. So you could keep brute forcing and looking at how quickly it goes.
Yeah. So typically the password space is all possible strings or all combinations, right? Try to brute force it is very hard. There are various password hackers try to do smart rules because humans have patterns. For this one, it makes it easy because first character, there are only this many combinations on your keyboard. Right? You try it, I don't know how many numbers are there, upper, lower case, all the symbols, all the numbers. It's actually, write the program fairly easy to iterate all of them. If you're wrong, it quit right away, so you can try again. Right? So very quickly you figure out what's the first character, then you move on to the second one, and eventually the complexity of you trying out character by character is much, much simpler than you try to brute force the entire password space, right? Yeah.
Sorry, this is also a nitpick, but the if condition is always true because there's single equals instead of double.
Sorry.
This is
A typo.
Yeah, there's a typo because the if condition is always true since there's a single equals instead of a double equals.
Oh, yeah. Let's say that it's not a C program. Yeah. Let's forget about it. There's C, there's JavaScript, there's functional programming, the equals are crazy. But yes, so you've got the gist of it. Yes. So this is almost like a termination channel, not necessarily timing. So when you terminate, you give a signal to the attacker that yes or no, this is correct or not correct. Having that signal makes the problem easier, right? So this is secret leak also, but nobody gives out the password directly, send it out, right? I'm not even doing the previous while loop, try to encode the password, send it out secretly, right? This is like a subtle bug that leak information, right? Okay, everybody got this one? Yeah? All right, let's go to the next one. So this is like super duper simplified RSA timing leaks. So I have a program F. Take the input, anybody can give this input because these APIs are public. And then there's a secret that I have. So what I do is I either skip once or have a long computation. I put 4 skips there. You can have more skips if you want to. So if either one of them is 0, I return fairly quickly. Otherwise, I took a long computation. There's a timing difference between this. So how would you go about figuring out what the secret might be? Anybody else? Think about this. Anybody in the back that have thoughts?
Does the program have the same runtime for different values of x?
Yes, correct. Yeah, so there is a differential attack, right? If I give it 0 or 1, if the time is different, it's very likely the secret is 1, right? You can measure the timing fairly precisely, right? So here, if you read about RSA timing attack, it's kind of sort of similar, but the computation is not that simple, right? Depending on the secret bit, 1 or 0, you are running a more expensive computation multiply or doing addition. But based on this timing analysis, the attacker would try to brute force the key bit by bit, by keep measuring the time. Right? So now, for timing attack, don't assume it to be, I can exactly precisely measure timing, because typically in a system the attacker interacting with, there are other factors, there are other programs running, there are other workload, there might be other microarchitecture features that you have to deal with. It's a probabilistic attack. You try many times. Eventually, with high likelihood, you might be able to recover the key. Yeah. All right, everybody got this one, yeah? Okay, so now we do more timing attack. So who's working on side channel attacks? There has to be, yes, great. If anybody have a question about this, ask the side channel person to explain. Okay, so this is microarchitectural difference that I used to tell people, if you ask me what do you work on, I said I work on compiler and above. I don't care about anything compiler and below. So this is actually something that compiler and below, in that most computer, if you're not working on team type embedded devices, most computers actually have cache, multiple caches, L1, L2, L3, and so on, so that you want to move data closer to the CPU, so things are faster. The further they are, out in memory, out in disk, it's a lot slower to actually read-write data. So cache is introduced to move data closer to CPU, right? With chips advances, you can actually put more cache closer to CPU as we go, right? So the problem here that we're introducing a timing channel, when I read a variable, the amount of time for me to get that value back, depending on whether this line of data has already been loaded into cache or not. If it's in cache very fast, if it's out in memory, it's going to take several cycles for the data to appear eventually into the register to have the computation, right? So this is the timing channel, and also there are lots of side channel attack exploit this. So I just want to show you one. This is kind of standard now in the Spectre meltdown age. They always use this attack to show you. Okay, let's set this up. So here I have, let's see, I have a big array. Let's call it probe array. Attacker also have access to it. So a lot of computers, program languages, infrastructures have shared data regions across different programs. This kind of, every time you share something with other users, there's a problem, could be a potential problem. Let's say that the attacker, there's a secret that the attacker shouldn't have access to. Only systems programs should have access to the secret. And then I have this program P, let's call it victim program. Somehow this victim program get to run a program that access this probe array indexed by secret. I time this 4096. This is the size of a memory page. When you read a variable, most computers load the entire page into the cache. So I just want to index which page to load by the secret. Right? So this program, actually, in the Spectre meltdown age, there are different ways to cause this victim program to run this. So again, the victim programs was not supposed to actually run this line, but for whatever reason, because of speculative execution or some other quirks in the microarchitecture, end up running this program. So now the attacker, knowing that the victim program have run this line ahead of time, now they are doing a probing attack where the attacker is going to one by one access every page of this probe array. Right? So now, if the attacker figure out some page access is much faster than other pages, it meant that that is probably the secret value, because that's a page has been preloaded into cache by this poor victim program. So this is a picture I took from one of the Spectre meltdown paper, I don't remember which one. So here, again, it's a probabilistic attack, right? The attacker has measured timing. You can see that there's a bit of noise up and down. So these are the pages that's not in memory. It took this much time to load the data into memory. And here is a very steep down peak here. It's around 80 something. That's very fast, right? So the attacker runs this experiment many times, then they can kind of figure out what the secret is. Right? So here the secret 80 something here. Right? So this is a timing attack. Again, this is secrecy leak. It's quite complex, but through observation and shared data, shared architecture, the attacker managed to learn secret. Right? Yeah, any question about this one?
So this is a real life attack that happened?
Yeah, so the Spectre meltdown, actually, people demonstrated that, yes. Yeah. This flash and load, this one flash and load, there are other methods too, right?
Yeah, I just asked a question.
Yes, in real life habit. So it's also interesting that in security, theorists actually talk to this here to work. When I talked to her, she was visiting CMU. We're writing about some paper shouldn't have gotten published. It was interesting. It was a paper. It was an attack on defender privacy. That got accepted, got a lot of news coverage, whatever. And Cynthia said, "Oh, this attack has been proven to be theoretically possible for years. And now they just, did a practical attack. So what's the point?" It's interesting that